Hello, now Ujwal and Shreyansh, we are going to talk about three-phase fully controlled bridge converter. The three-phase fully controlled bridge converter has been probably the most widely used power electronic converter in the medium to high power applications. Three-phase circuits are preferable when large power is involved. The controlled rectifier can provide controllable output, put DC voltage in a single unit instead of three-phase auto transformer and a diode bridge rectifier. The controlled rectifier is obtained by replacing the diodes of the uncontrolled rectifier with thyristors. Now I am going to talk about operating principle of three-phase fully controlled bridge converter. In this, the following assumptions were made. The three-phase voltages VA, VB, VC are balanced. For the thyristors, forward resistance is 0 and reverse bias resistance is infinity. For all the thyristors, triggering pulses are coming at exactly 60 degree. The DC current is ripple free. A three-phase fully controlled converter is obtained by replacing all the 6 diodes of an uncontrolled converter by 6 thyristor as shown in figure 13.1a. For any current to flow in the load, at least one device from the top group T1, T3 or T5 and one from the bottom group T2, T4 and T6 must conduct. It can be argued in the case of an uncontrolled converter, any one device from these two groups will conduct.
Then, from symmetry consideration, it can be argued that each thyristor conducts only for 120 degrees of the input cycle. Now the thyristors are fired in the sequence T1, T2, T3, T4, T5 and T6, then back to T1 with an interval of 60 degrees between each firing. Therefore, the thyristors on the same phase leg are fired with an interval of 180 degrees and hence cannot conduct simultaneously. This leaves only 6 possible conduction modes for the converter in the continuous conduction mode of operation. These are T1, T2, T2, T3, T3, T4, T4 and T5, T5, T6 and then T6, T1. Each conduction mode is of 60 degrees duration and appears in the sequence mentioned. The conduction table of figure 13.1b shows the voltage across different devices and the DC output voltage for each conduction interval. The phase diagram of the line voltages appear in figure 13.1c. Each of these line voltages can be associated with the firing of a thyristor with the help of conduction table 1. For example, thyristor 1 is fired at the end of T5, T6 conduction interval. During this period, the voltages across T1 was VAC. Therefore, T1 fired at an angle alpha after the positive going across VAC. Similar observation can be made about other thyristors. The phasor diagram of figure 13.1c also confirms that all thyristors are fired in the correct sequence with 60 degrees between each firing. Figure 13.2 shows the waveforms of different variables as shown in figure 13.1a. To arrive at these waveforms, it is necessary to draw the conduction diagram which shows the interval of conduction for each thyristor and can be drawn with the help of phasor diagram of figure 13.1c. If the converter firing angle is alpha, each thyristor is fired alpha angle after the positive going zero crossing of the line voltage with which its firing is associated. Once the conduction diagram is drawn, all the other voltage waveforms can be drawn from the line voltage waveforms from the conduction table of the figure 13.1b. Similarly, line currents can be drawn from the output current and the conduction diagram. It is clear from the waveforms that the output voltage and current waveforms are periodic over 1/6 of the input cycle. Therefore, this converter is also called the 6-pulse converter. For our simulation, this is the output we get. So this is how a 6-pulse phase converter works. Thank you.